Okay, good afternoon. Welcome to EE222, Digital Logic Design. We were looking at some operations. With regards to binary numbers. Give me a second. I will soon investigate if we do have any students who are participating online, because originally what had happened was, because just before we started the semester, the regulations from the department, the Ministry of Health, was that we can't occupy the lecture room to full capacity, because the regulations with regards to social distancing was still intact. And the way around this, the workaround was that we would have I hope I'm in the right room. The workaround was that we would have students who would participate online, all right, and some students would attend. But I think those restrictions have been lifted, so there is no social distancing required. And I will investigate, and if there's no one in the region, if everybody's here in Fiji, then they should be attending the lectures, all right? Okay, let's continue with EE222. All right, guys. So let's flip over to the document camera. We're flipping over to the document camera. All right. Okay. So the particular topic which we left off with yesterday afternoon was in relation to binary addition. All right. Now, let's have a look at binary subtraction. Let's have a look at binary subtraction. So let's put today's date. What are we on? We are on week 2, lecture 3, and this is the 31st of March 2022. Okay. So binary subtraction. Now, before we begin binary subtraction, we need to look at the concept of how subtraction is done. So let us say we want to do 35 minus 18. So the way we go about doing 35 minus 18 is 5 minus 8 is not possible, because 5 is a smaller number and 8 is a larger number. So we go to the neighbor, we borrow a 1. Yeah, remember this? We borrow a 1, and the remainder on that side is 2. So we do a 15 minus 8, which gives you a 7, and 2 minus 1 is 1. All right. Now, the same concept applies in binary. The same concept applies in binary. Let's say in binary you have the number 1, 1, 0, 0, and you want to do a subtraction of 0, 1, 0, 1, right? 0, 1, 0, 1. All right, so this is a straightforward subtraction. Well, 0 minus 1 is not possible. 0 minus 1 is not possible because 0 is a smaller number, smaller bit, 1 is the bigger bit. So we go to the neighbor. We can't borrow from there either because that's a 0. So we go to the neighbor, we borrow from this neighbor, cut, that's a 0 now, that becomes a 1, I mean a 1, 0. Now we borrow from this neighbor, that becomes, if we remove a 1 from there, that becomes a 1, and then this becomes a 1, 0, right? So 1, 0 minus 1 gives you what? In binary. Now think about it. 1, 0 minus 1 is not 9, right? 1, 0 minus 1 is a 1, you got to think of it in terms of the odometer. If you have 1, 0, and then you don't roll it forward, you roll it backwards, you'll go back to a 0, 1, right? You'll go back to a 0, 1. So 1, 0 minus 1 is a 1. 1 minus 0, that's quite straightforward, is a 1. 0 minus 1, again, it's not possible. So what do? We cut this 1, we cut this 1, and then a 0 remains left behind over there, and we borrow a 1, so that becomes a 1, 0. 1, 0 minus 1 is a 1. 0 minus 0 is nothing, right? So we are left with 111. Now, let's have a look on the right-hand side. 1100 is what? 1100 is what number? 12? Yeah, well, what is it, guys? 1100 is 12, is that correct? 101 is what? 5, and 111 is 7. So our answer comes to be correct, right? Our answer comes to be correct. So we are happy that our binary subtraction works, right? We are happy that our binary subtraction works. Now, the idea here, guys, the idea here is that the way our machine works is that when you punch in your calculator, and that's part of your work here in EE222, that we are working towards building a calculator, an arithmetic logic unit. Part of your work in building a calculator is that when you punch a number, to you see it as decimal. The machine converts it to binary, first step, right? You let's say punch two numbers, A plus B, converts A into binary, converts B into binary, does the number crunching in binary, then converts the answer back into decimal to display to you, so that you can see the answer on your calculator. So that's how the system works, all right? Okay, so that's what we've done. So that's what I'm showing to you on the left and the right hand side. Now, another important point about subtraction. Subtraction is, in fact, I want you to rethink the way we do subtraction. Because doing subtraction, if you look at it, it was very messy. Addition is quite straightforward, right? Subtraction was very messy. Addition is quite straightforward. Because in subtraction, you had to go and borrow to the left, and if it's far off in this particular problem, we had to move twice before we could borrow, all right? Now, subtraction is, in fact, another way to rethink subtraction. Going this way, doing binary subtraction in your normal operations isn't going to work. So we've got to think of another way to do it. So even subtraction is addition to a negative number. Okay? Subtraction is addition to a negative number. What do I mean? Let's look at x minus y. Over here it was x minus y equals z. Right? Let's say z is equals to x minus y. Another way to think of this is x plus negative y. X plus negative y. All right. So in real life, our calculators handle subtraction in that manner. Once we are able to do addition and once we are able to do subtraction, from there onwards, everything is built upon these two building blocks. Because multiplication, what can you tell me about multiplication? What is the relationship between multiplication and addition? Yeah, it is repeated addition. Multiplication is repeated addition. What is the relationship between subtraction and division? It's repeated subtraction, right? Of course, there's a remainder in the end, but it's a repeated subtraction. So the same applies over here. So once we are able to do addition, and once we are able to do subtraction, we can go ahead. But the method I just showed you there, that only works when we do it. Machines aren't able to do it like that. They can't go and borrow. They become haywire if they start to borrow. And it takes up too much computational space to make a machine to go and do borrowing. So we've got to do a faster way. What is the faster way? To add to a negative number, which brings us to our next topic. How do we represent negative numbers? How do we represent negative numbers? All right, in binary, of course. How to represent negative numbers. All right. The answer is, what is the answer? Anybody knows this from the tutorial? There are many ways. There are many ways to skin a cat or bake a pie. Right? Okay. Just off the top of my head, the famous ones. There's sine and magnitude. There's 2's complement, IEEE, IBM. There are some other standards. There are many other standards to represent negative numbers. Right? We won't be able to teach you. If I start teaching you all the methods, then this whole class will be called not EE222 digital logic design, but EE222 representation of negative numbers. Right? Okay? So there is, when you start getting into these things, there are many, many methods. Okay? So at every point in time, everyone has got one particular method which has got a limitation. Every method has a limitation to represent and store negative numbers in binary. Maybe I didn't finish that sentence to say in binary. So some of the famous ones which we want to start off with at least are sine and magnitude, and number 2 is the complement method. All right, so let's start off with the first one. Sine and magnitude. All right. Let's start off. This is a very simple one. Let us consider an 8-bit Gamba. Right? Okay? Let's look at this 8-bit number. So 8-bit number, let me just quickly draw. You know, I hope you guys are not as rough in your drawing as I am. Is that 8? Right. So let's say this is bit 0, bit 1, 2, 3, 4, 5, 6, 7. Oh. Rightio. Okay. So the way it works is the most significant bit, this fella here, which is our most significant bit, right, that stores sign information. And our seven by LSB, the 7 least significant bit, the least significant bit side, stores magnitude. All right. Now, the sign information is better known as the sign bit. And if the sign bit is 1, that means the number is negative. If the sign bit is 0, obviously our number is positive. Okay? So that's how the scheme works. Very simple scheme. You reserve 1 bit for, you are reserving 1 bit for the purpose of sign information, whether it's positive or negative, and therefore you are reduced to only 7 bits where you can actually store the real information about the magnitude of the particular number. All right, let's now consider an example. Let's now consider the number. Let's start off with a positive number, right? Let's start off with the number positive 98. Okay, and we want to convert it into sign and magnitude. Obviously, the key piece of information whenever we're dealing with negative numbers is the amount of space available. In what we did earlier on, yesterday onwards, was what is called natural binary. All right? When we say natural binary, it means you just convert a number directly to binary. Right? You don't worry about if it's 6 bits, you just leave it as 6 bits. If it's 3 bits, you leave it as 3 bits. If it's 11 bits, you leave it as 11 bits. You don't need to conform. The moment you get told that this is negative number, sign in, so you have to conform to some rules. All right? So 98, let us say you want to convert positive 98 into, I hope it fits in 8 bits. Okay, let's say it's 8-bit number. Right? Let's say it's 8-bit number. Okay, now what is the first thing we notice about the number? What can you tell me about the sign? Positive. It is a positive number. All right, it is a positive number. Therefore, our sign bit is equal to 0. All right. Now, let's look at the magnitude bit. In order to look at the magnitude bit, what we have to do is we have to take the absolute value of that 99, which we knew is 99. We then convert 99 to binary. And can somebody tell me what 99 equals to? Can you guys do it quickly? Yeah. Anybody got a fancy calculator which can do conversion to binary? Yeah. You know what the problem is? And I think I'm going to start a business on this. The high schools, they all sell Casio. And Casio is a shit calculator. Right? It's useless. It's useless, especially for students who want to do physics, mathematics, engineering. The guy who does, so everyone, how many of you guys own Casio? I'm sorry for you guys. Right? The better calculator is Sharp. You can buy Sharp from me. Okay? No, I'm joking. I don't have that money. Right? Okay? Sharp can handle matrices. Sharp can handle doing determinants of matrices. Can do complex number matrices. Sharp. It's the sharper calculator. All right? Okay. But nobody sells them. That's unfortunate. Don't give my business idea, right, away to anybody. I'm going to sell it first. Okay. All right. So yeah, Sharp can do this number, binary addition, binary subtraction, conversion to 2's complement. So luckily for you guys, you can check your answer in the final exam using the calculator. You have to do it by hand. All right. Okay. 99. What is it, guys? 99? Oh, sorry. Was it? Oh, sorry, guys. I thought 98. 98. Sorry, man. Yeah, 98. What do we get? Right, thank you. Thank you. 110010. Right, that's in natural binary. Right, that's good. So first you find your answer in natural binary. Natural binary, okay, you can note this word down, natural binary. Natural binary means whatever answer comes, right, wherever when you do the divide by 2, remainder divided, wherever you find the 0, you stop there. Now we count the bits. We count the bits. We have 1, 2, 3, 4, 5, 6, 7. There is an 8th bit, which is supposed to be your sign bit, which will be a 0. Right? Therefore, our final answer, positive 98, is equal to, okay, so let me just label this. This is your sign bit. Positive 98 is equal to 0, 1, 1, 000, 1, 0. And then what we do is, check this out. We say base 2, and then sometimes some people say sign and magnitude. Can you see S and M? To indicate that is the standard which we are using. We're using sign and magnitude. All right? Okay? Let's have a look at another one. Let's do another example. Let's do the same number, but let's flip it to negative 98. And we want to do 8-bit. Now, very simple now. Sign bit will be what? Sign bit will be, well, it's a negative number, therefore it is a 1. Your magnitude bit. Your magnitude bit, how many bits do we have, guys? How much space do we have? If it's an 8-bit number, 1 bit is occupied for your sign bit, how much space do you have left? 7 bits. All right? Now, so 7 bits, so we take the absolute value of negative 98 and we get 98, and from our earlier problem we know that this is 1, 1, 1, 1, 0, 1, 0, right? So your final answer, negative 98, will equal to, I'll use a different one, right, over here, and I'll say this one here is that guy over here, and we say 1, 1, 1, 1, 0, 1, 0, and then we say sign and magnitude, 2 sign and magnitude, right, and this here comes from that there. All right. Okay. Now, let's talk about some of the limitations. Let's do one example, one more trickier example. That was very straightforward. That was very straightforward. Now, let us look at the number. Let us look at negative 136, and this is when we start to realize where the problem lies, and we want it in 8 bits. All right? Okay, so our sign bit, it is a negative number, so therefore negative number sign bit will equal to 1. Right? Set? Okay. Now let's look at our magnitude. Magnitude, what do? We take the absolute value of 136, and which is equals to positive 136, and we convert that to binary. Can you guys go ahead and do that? Because we've done enough conversions to binary. How many of you guys attended the tutorials? Anybody missed out on the tutorials? Make sure you attend the tutorials, all right? because we've done a lot of those problems in our tutorials. Right, what do we get, guys? 136. Give me the binary number, natural binary. I'm not asking you to assemble anything now. What do we get? (136) in natural binary is, what do we get, guys? Sorry? Double one? 1? 000, yeah, continue. 1 again. Again 4 zeros. Right. 100 followed by 100 again. Okay, so 100 followed by 100. That's in base 2. Now we have a problem. Now we have a problem. Because so maybe note it down, we have a problem. Where is our problem, guys? Our sign and magnitude system had specifically asked that we convert negative 136 into an 8-bit number. But the natural binary part comes to 8-bit in itself. So we have the answer, we propose possible, we might go in this direction. It's not the answer. We'll say, hey, 1 is our sign bit, that's from here, and our magnitude is 100, 100. But hey, when you count that, that's 9 bits. So this possibly becomes either this or that becomes overflow. So from this particular example, what can you tell me about the limitation of sign and magnitude? What is the limitation? Sign and magnitude is constrained by the number of bits. Because if you have so in this 7-bit number, now I ask you a follow-up question, and maybe I might not write it down, I'll ask you a follow-up. So what is the limitation? The limitation is that it is constrained by the number of bits. If you have an 8-bit system, example, if you have an 8-bit system, 1 bit is reserved for the sign, therefore you have 7 bits for magnitude, right? 7 bits for magnitude. Everyone happy with that? Okay, now, if it's 7 bits for magnitude, your number range becomes smaller. What is the largest possible number which you can achieve using an 8-bit sign and magnitude number? Give me that. 100 and what? Okay. What is the largest number? Largest. Using an 8-bit. Using an 8-bit. Looking at this example, now you're starting to think something. And looking at all the 3 examples which you've done, they were all 8 bits, by the way. What is the largest possible number? What is the largest possible number? So, largest possible number would be a positive number or a 0 number? Or a negative number? Largest possible number would be a positive number. So, it will start off with what? 0 followed by what? All ones. Yeah? So, if it's all 7 ones, because the first has to be 0, positive, followed by 7 ones, what do you get? 127, right? So it's 127 is largest possible number. What is the smallest possible number? It will be again 1 in the magnitude, in the sign, followed by all ones. So negative 127. So the range is negative 127 to positive 127, right? Okay? That is our constraint. So what we are trying to say over here is, when we use sign and magnitude, and in fact the whole binary system is like that. you are constrained by the number of bits. But over here, what happens is that one particular bit gets used up in your sign in magnitude. Okay, all right. All right. So let's have a look at range now. Range of sign and magnitude. All right. Number of bits. Smallest number. Largest number. I'm not going to do all of them. I expect you to do some of them. All right. Some of them on your own. So 3-bit, I'll leave it to you. 4-bit, I'll leave it to you. 5-bit. 6-bit. Okay, let's attempt 5-bit. All right. So 5-bit. Smallest possible number, if it's a 5-bit, would be for the negative and the positive. Oh, sorry. So smallest possible number will be a negative number. The negative number will always have a 1, right, for the sign, and then 4 ones for the magnitude. And the largest number will always be a positive, obviously, which will be a 0 followed by 4 ones. This is what? Negative 15. This is positive 15. Now, I'm going to leave some space blank over here, all right? And I want you guys to do it. Fill up all the blanks for your homework, all right? Okay. Let's try 7-bit. Negative will be 1 followed by 1, 2, 3, 1, 2, 3, 4. Over here it will be a positive and it will be a 0. Okay, sorry. We remove this guy. Yeah. 0, 1, 2, 1, 2, 3, 4. Yeah? So this becomes what? We just did this. There will be what? Negative? Negative what? 6 ones in a row is what? 63. This is positive 63. Right? Fill up all the blanks. Okay? All right. Now, what can you tell me about, by looking at these two, right? By looking at these two, for a 5-bit number, the smallest number is negative 55, negative 15. Largest number is positive 15. For a 7-bit number, the smallest number is negative 63. Largest number is positive 63. Can you give me a mathematical equation to describe the smallest and largest numbers? Yeah, something along those lines. You're on the right track, because it's always powers of 2. So obviously, it's got to be powers of 2. Somebody? Anyone? Yeah, what do you get? All right. So for the smallest number, so I'm going to put it here. For the smallest number, we have 2 to the power of n minus 1, and then of course we want to put a negative sign there. Right? Okay, and over here we have positive 2 to the power of n minus 1. All right? So if I give you, let's say for example, I say, hey, I am talking about a 16-bit number. In sign and magnitude, can you calculate for me what is the smallest number? Sometimes I won't write all the examples. Sometimes I'll just ask you verbally. So it's your duty to jot it down. All right? If it's a 16-bit number, what is the smallest possible number and what is the largest possible number? Given that we have already found this equation. Where n is the number of bits. Okay, sorry, no. This will be n minus 1 Yeah, minus 1. Thank you. Here, n minus 1. Where n is the number of bits. So 16-bit, smallest number. Because obviously we can only use 15 bits from that 16. What do you get? Negative 116 bits. Yeah, 16 bits. What do you get? Sorry? 32768 for the negative number, right? And obviously for the positive highest number, it's positive 32768. All right, so you should know how we get that. All right, so fill up the table to see the pattern and so forth. Fill up the table using this method, and you can also find the answer contrary using this method. All right, guys. Now let's do one more thing before we knock off. We want to apply summing. Apply sum to achieve subtraction. So remember, I was saying x minus y is same as x plus negative y. So let's, for example, I was referring to 7 minus 4 is the same as saying 7 plus negative 4, which is equal to 3. So let's now apply using 4 bits. Sum of S and M to achieve subtraction. All right, so 7. Let's now first talk about 7. 7 is, in 4 bits, would be, it's a positive number. What do we get? 7, let's choose some easy numbers so we can, yeah, 7 in 4 bits gives what? Positive 7, which is 0,111. That was positive. And in order to achieve the negative 4, obviously the first bit will be 1. The remaining bits will be the magnitude, which is 100. Now we want to do an addition over here, right? Because we are adding to a negative number. So we have 1 plus 0 is 1, 1 plus 0 is 1, 1 plus 1 is 1, 0. Write down 0, carry 1, 1 plus 1 is 1, 0. Write down 0, carry 1. So our answer, because it is 4 bits, this becomes overflow, right? And our 0011 is stored. And 0011 is equal to the number 3. And we have the correct answer. You see how that was done? With sign and magnitude. So in order to do subtraction, we have to convert the second number, the subtrend, to become a negative number. All right. Let's look at another example. What time is it? Does anyone have the time? Anyone has the time? Okay, I don't think there's a class in this room, right? We can continue, right? Okay. All right. 6 minus 2. All right, 6 minus 2. Let's do this one. Again, in 4 bits. 6 plus negative 2. Right? So 6 is a positive number. And that would be what? 6 is what? That will be 0. Obviously, I'm reserving the first bit for my sign because it's a positive. And the number 6 is 110. And then my minus 2, it's a negative number. So I put a 1 over there. And in order to put the negative number, it's 010. So 0 plus 0 is 0, 1 plus 1 is 1, 0, carry 1, 1 plus 1 is 1, 0, carry 1, right? 1 plus 1 is 1, 0, carry 1. Am I correct there? Right? So we end up with this 1 becomes my overflow, and we have this as stored. 0, 0, 0, 0 is equal to 0. So we have a problem. This is wrong. Right? So what do we get from this? And this was a simple problem. This was a simple problem. Was there any issue over here? 6 minus 2 should have given me a positive 4. But positive 4 is within range. Positive 4 is within range. It's within a 4-bit number range. Right? Well, 3-bit. Positive 4 can be achieved with 3-bit. So it was possible to represent positive 4 by doing in sign and magnitude would have been what? 0, 1, 0, 0. Right? But this thing has made a terrible error over here. So what we conclude from this is that sign and magnitude is unreliable for arithmetic circuits and systems. All right? Okay? Yeah. So sometimes when I'm writing it down, I'm calling it out as well. If you can't see it, you can hear me. All right? S&M, sign and magnitude, is unreliable for arithmetic circuit system. So if you make a calculator where you do addition or subtraction, especially using the sign and magnitude system, you will start to get the wrong answer. All right? Okay. All right, guys. So that's it for this evening. Next week on on Tuesday, Monday we will have a lab. We will begin our labs on Monday at 9 o'clock. For those of you who have signed up for the labs. We will also next week announce the sign-ups for EN001. We will also have multiple Zoom sessions for EN001. So for those of you who are in engineering, not BSc, not Bachelor of Science, Bachelor of Engineering students, you will be watching some Zoom where I'll be communicating with you with regards to what is expected of you. All right? Okay. That's it for this afternoon. We will see you next week in the lab.